Hello, Learn STEM. In this video, I'm going to be showing you some statistical testing. This is in Excel, but if you're on Word, then that works too because they have all the same code and everything. So everything is the same, like the methods to do things and like the equations and all that. It's all the same because this is just copy and pasted from Google Sheets. Did I say that or did I say Excel? But anyway, Excel and Sheets are the same, and this is copy and pasted from Sheets because for some reason on this computer, it's always lagging. I'll show you later because I'll switch over there for a second to show you something. But we're going to start off with null hypothesis and alternative hypothesis. Null hypothesis is there is no statistical difference between something in your data. It's different for every experiment, and I'll show you an example later. But alternative hypothesis is the opposite of this. It states that there is a statistical significance in your data. Hopefully that will make more sense later. But right now we're going to start off with variance. This tells you basically the spread of your data, like how far apart it is and everything like that. And it's pretty simple. For everything you're going to see on Excel or Sheets, it starts with an equals if it's an equation, if you want to do something with it. So for variance, it's VAR, and you will see that for like all of these, it's pretty easy to determine what the code for it in the beginning is going to be. Like variance is VAR, the chi-square down here is chi-test. It's very simple. So first I'm going to put in, it's pretty helpful down here. It shows you what you need to input. And Sheets, I believe it doesn't do that. But here, your first group of numbers and your second group of numbers, you can do that too. But right now we're going to do just one. So it's going to tell you the variance of all those blue highlighted ones right there. And you can even do, instead of doing the equals VAR parentheses on your group 2, you can just go into this little square and drag it over. And you can see that in this code, it's the same thing, except it uses the C column. It's really helpful. And so that's what your variance does. In t-test, there's a little bit more to it. Equals t-test, it's the same. It's not the same, but it's pretty easily distinguishable, which is great. For this one, it has more stuff. Like I said, you still have your array 1, array 2, because this compares two groups of things. It compares two things. So you're going to want to put in your first and comma your second group of numbers. And then there's two more numbers after that. Tails, you can see there's one-tailed or there's two-tailed. And one-tailed, it looks for either an increase or a decrease. I know that's like hard to, it really doesn't make sense to me. But most of the time you're going to be using a two-tailed distribution because that means it looks for either. It's really most used. But one-tailed, it's looking for an increase only or a decrease only. So for this one, we're just going to use a two-tailed. And then this last one, type, there's 3 types, as you can see: paired, 2 sample equal variance, and 2 sample unequal variance. Paired would be values that are kind of linked together. Like, as an example, you test your flexibility before taking gymnastics and taking it and after taking gymnastics. It's like a before and after. That's a pretty common way you see this used. And for this one, it's not very specific, obviously group 1 and group 2, but let's just say it's not paired. And then 2 sample equal variance is where you assume that the variances are the same. And since this is the same numbers, we know that the variances aren't the same, so we can't put in the equal variance. It's going to give us different data. So for this one, 3 unequal variance, it pretty much is what it sounds like. It's you use this one when the variances are not the same. And what this is going to return, you might be like, what is this number? Well, it's your t-test p-value. And you'll kind of see that a lot in statistical tests. Your p-value tells you whether your data is significant or not. And more of what I mean by that is the smaller your digit is, means the more similar your results are. Obviously, with a group that's pretty simple like this, you can kind of tell that the results are pretty similar. But to go off of that, you'll see something called like the p-values, right? And it's not exactly this because this is specifically for a chi-square, and it has degrees of freedom and all that. But usually, statistically significant is if your p-value is less than 0.05. And this being 0.06, it would not be counted as statistically significant. So you would accept your null hypothesis. Like I said, there is no statistical significance. And obviously for like actual experiments, your null hypothesis and your alternative hypothesis would be more specific, more catered to your actual experiment. But these, there's nothing really going on. It's kind of group 1 and group 2. So that's why those aren't that specific. The next test is your chi-square. And basically you get it by, as you can see from this formula, adding up this formula, which is your observed values minus your expected, all squared, all over your expected values. So with this, it's just numbers for a die. So it's counting how many times each number is rolled. So it has 1, 2, 3, 4, 5, 6 on a standard 6-sided die. And your expected values is basically, it's like if you were if you didn't know, if you had no experience with a dice, then I guess, yeah, if you had no experience with a dice, you would assume that all 6 sides would like evenly be landed. But in reality, we know that's not the case, but expected, that's why all of these are the same number. It's also the same with another example that I'm going to show you after this one. But here, it's been recorded all of the numbers that were actually observed. So this person actually did roll their die 120 times, which is what you get when you add all of these up. And speaking of adding them up, I'm going to show you how to do that. Sum equals sum and your range. Oops. Here. That's not sum. There you go. Sum. And that equals 120. And then you see if we drag it over here, it has the sum of C26, the C column. So as you can see, they are the same number, and there is a reason for that. They have to be the same number, your observed and your expected. They have to be the same number. And now we are going to go on to the chi-square. This one's pretty simple too, equals chi-test. And how you're going to do this is it has these right here. It's very helpful. Actual range, which would be your observed, and then your expected range. And this is going to give you a p-value for chi-square. And you can see up here that, like I said earlier, 0.05 and below is statistically significant. But you're not going to see these numbers up there because there's a thing called degrees of freedom. And degrees of freedom is basically the number of categories you have minus 1. So in this one category, it's clearly listed right here. But 1, 2, 3, 4, 5, 6 would be your categories minus 1, so 5. So over here, you would look for degrees of freedom of 5. But the chi-square doesn't return these numbers down here. It returns the p-value, which is already up here. And to make that make more sense, I'm going to show you another example, because right here, you're not going to find this. If this went all the way down to degrees of freedom of 5, you're not going to find this small number in the middle right here. It's less than 0.01. So that would mean your data is statistically significant. And I know I made that sound really confusing, but I promise I'll clear it up. To word it a little bit better, because I don't think I did a very good job, when you're calculating chi-square manually using this formula that I talked about earlier, then you'll get a number like this in here, not on any of the axes, I guess. Because here it's immediately skipping to the p-value. So I'll show you how calculating the chi-square would work. Okay, so this is a picture of some M&Ms, and it's kind of like the dice. If you've never had M&Ms, you would just assume that, oh, since there are 1, 2, 3, 4, 5, 6 colors, then each one would appear the same amount of times. But you can see from here, that isn't always the case. So in order to calculate the observed and the expected, the differences between them, I used a chi-square. And you can see up here that the null hypothesis is that there is no significance between the number of expected and observed M&M colors, which is what someone would initially believe. And then your alternative hypothesis is that there is a significant difference between the number of expected and observed M&M's colors. So here you can see that I recorded all the numbers from the previous slide, and it equals 101. And then I used percentages of the colors that were expected, and I came up with my own list of expected M&Ms. And as you can see, they add up to 101 because you always need them to be the same. In order to do this, since all of these rounded down to a number, then I had to round up on 1 to make it equal to 101, but you can do that because they have to be equal. And then the degrees of freedom, like I said, it would be n minus 1, and n is your category. And since there are 6 colors, it would be 6 minus 1 with a degree of freedom of 5. And then here I use the equation like you saw earlier, but this is missing the sigma where you add them all together because it's on the bottom. But I did my observed minus expected for my red. So observed minus expected, which would be 7 squared, 49 over 12, which is your expected value, equals 4.08. And I did that all the way down. And at the bottom here, I added up all my values. And using a chart like I showed you earlier, it stated that to be statistically significant, the value should be 11.07. And mine was greater, which meant that my values were statistically significant, which meant that I could reject my null hypothesis and accept the alternative hypothesis because there was a significant difference between all the colors of the M&Ms. Okay, now we're moving on to ANOVA. And I have here Google Sheets because this is the one that I'm going to show you on Google Sheets because I didn't want my screen to glitch out for this whole video, so I copy and pasted everything in Excel. But I'm going to show you how to do an ANOVA on Google Sheets. And all of these values that you see are just values that I copy and pasted from Sheets that you'll see when I switch the screen. Okay, so this is Google Sheets where I'm going to be showing you the ANOVA. So right here you have 3 different trials, and in order to actually start the ANOVA, you're going to have to install an extension on here, and you can read the instructions here, but in order to do that, you will click on the extensions and add-ons, and then get add-ons, and then you'll find that there is something called the XL Minor Analysis Tool Pack in these add-ons, and it is free. And I have it right here. And so in order to start this, okay, yeah, that's the glitch I was telling you guys, but in order to start this, I'm going to highlight all of those 3 trials and all of their information like I showed you, and I'll be back when I can do that without this glitching. Okay, so now that I have it highlighted, you don't have to highlight it before you open the tool pack, but it's helpful and I'll show you why. I'm going to open it now and start. And you might have to wait a little bit, but you're going to open the first option. It's the ANOVA single factor right here. And since I have this part highlighted, I can just click the input range and it'll autofill it for me. And the alpha, like I showed you in the p-values, is going to be 0.05. And your output range, you can put whatever you want. I'm going to put E3 so I can, so it actually outputs there onto E3. And columns and rows, I'll show you what that means. Columns go up and down. So it just means that it'll take each data up and down like this instead of rows, because if we did rows, then it would do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 trials instead of the 3 that we were looking for. So we're going to choose columns. One second. Okay, sorry. I keep forgetting that you have to do this, but since I have labels here that read trial 1, trial 2, and trial 3, you have to click this check mark that says that there are labels in the front in the first row. So since I put that in, you can see that the previous ANOVA single factor that was here got changed to these, the trial 1, trial 2, and trial 3. And for each one, it counts all of your data and it gives you your variance, your average, a lot of good stuff. And right here, right here, it shows you your p-value, which is 0.002, which means that this data is statistically significant. So this ANOVA is a really easy way to figure out if your data is statistically significant because it's pretty automated. It does it for you. So it's very helpful in order to find out your p-value. Another way to kind of explain the p-value is kind of how correct your null hypothesis is, because you'll notice like in the M&M thing that I showed you, it is assumed that null hypothesis is always correct. So if this p-value is lower, it means that you're disproving that, and you can later say that you can reject your null hypothesis or accept your alternative one. So finally, we're back in Excel and we're going to do the correlation test. And this one's really simple. It is exactly what it sounds like. It's to show if some data is correlated to another. For example, this one, age and your visits to the doctor. To find out if there's a correlation between that, you would do equals correl, I believe. Okay, equals correl your first array of numbers, and then comma and your second array of numbers. And then this data, I'll just show you. It gives you this number, and right away I can tell that this means that there isn't really a correlation. And so I'm going to graph it out and explain to you what I mean by that. So I just made a quick graph right here, doctor visits to doctor versus age. And all of these are the data that's right here. And as you can see, the dots aren't really lining up with the regression line. And that means that there isn't really a correlation because these dots are these data points are kind of all over the place. And like I said, I could tell from this number that that was going to be the case. And this is because it's your correlation number, your R, the closer it is to 1 or -1 means the closer your data points are going to be to your regression line. And I have another example of that later to kind of give you another example. But here I also have R squared tells you how much of the data can be explained by the regression line, right here, I squared R by just putting in the code right here, B58 squared, and it's also down here, R squared. So this means that about 14.1% of the data can be explained by this regression line, which makes sense because it doesn't look like these dots are really following the line. Yeah. You can also tell that this line is going to be going somewhat up because this correlation value is positive. It kind of works in the same way that a slope does, because it's not that positive. But I'll show you another example, like I said. So now I'm going to tell you about my research project and the statistics test that I used in order to deal with my data. So me and my teammates are testing hyperglycemia and its effect on Standardophytus elegans fertility. And this table, it's none of the statistics test. It's just me trying to organize our data. And what I have here is the different concentrations of glucose that we exposed our C. elegans to in order to get them to simulate hyperglycemia with them. And for each plate, we have three worms, eggs that we counted on one side of the plate, and then another 3 on the other side. And this is me just collecting the data. And in this next column, I average the plates out of 3. I average these 3. So this would be an average of these 3, and then this would be an average of these 3. And then in this final column, I average the averages in order to get one single number. And using this, I reorganize the data. So these first 3 numbers are the same as these because they are under the 0 millimolars of glucose, and then the same for 25, which are these, and then 50, 75, and then 100. You can see that they're similar, but I just made them more horizontal because it made more sense to me. And in doing this, it was more easy for me to do an ANOVA, which is what I did over here. And you can see that the groups are the concentrations, and count 3 because there were 3 trials for each one. And down here, you can see that my p-value was 0.00002, which means that it was statistically significant, and that there is a relationship between the increase in glucose concentrations and the decrease in Standardophytus eggs, which means fertility. And finally, here is the correlation, another correlation example that I told you about to make it make more sense. Here's just another, it's the same data, I just moved it down here again to make it look better and make it make more sense on the sheet. So these are all the same numbers, and I just plotted them out, like you can see, and there's clearly these data points are closer, and you can see more of a decrease that makes sense. You can see more of a decrease than the previous one. You can kind of make out that it's increasing, but the data points are kind of all over the place, which is reflected by this number 0.3748. But in mine, the correlation is a lot closer to 1, being negative 0.9255. And the negative, like I said, it means that it was decreasing. And since it's closer to 1, it means that these points are more accurately reflected in the regression line. And R squared right here, 0.8565, as you can recall, that means the percentage of your data that can be explained by the regression line. So in this one, about 85.7% of the data can be explained by the regression line. So I have these two tests, the ANOVA and the correlation, and I didn't do a t-test because the t-test required only two. It required two things to compare, and like I said, I have 5 groups that I wanted to compare, and then I didn't do a chi-square because that was observed minus expected, which wouldn't work for this experiment. So that's all. I hope you enjoyed. And you can listen to Learn STEM on Spotify, Apple Podcasts, YouTube, Anchor, anywhere you listen to your podcast. And you can also follow our Instagram, our Twitter. We're a lot more active on Instagram, and we post a lot of different things. I posted like an edit. And make sure to check out our other videos because I also just posted a vlog of me and Liam and Melania going to regionals for the academic club. And thank you for watching again, because guess what? I filmed this video already, but while I was switching screens to like show you my M&Ms or whatever, I forgot to change the screen share. And so for the rest of the video, it was just like blank. So I had to re-record it, and this is me re-recording it. So hopefully there are no problems with this and it goes up. So thank you again for watching, and I'll see you next time.